So we're going to continue talking about the thundering herd situation. Now, we didn't tell you guys what sort of a situation we were, moving from before, but this is what it is. Now, last time, the thundering herd of threads were racing towards this lock as they were created. So this gives the first few threads that are created the advantage of getting to the lock first. So you're never going to see a 1 or a 5 be the last one through the lock. So we're going to change things a little bit, and we're going to make use of a barrier so that they have all had a chance to be created before they're released at the lock. So imagine horses at a gate at a race. Anyways, so we're also going to add on the ability to see which thread makes use of the lock first.
Okay. Yeah, so we're going to use pthread barrier init basically to set up, and we'll use pthread barrier init, and we'll use pthread barrier destroy. These are just bookkeeping. You have to do this in order to use a barrier. Now, what's important here, again, we can pass null to that attribute, but this count is very important because that tells how many threads have to wait at the barrier before the barrier releases. So if you set that to a number that doesn't ever arrive, like you set the number 10 and only 8 threads ever wait on the barrier, those 8 threads will never be released. They'll hang there indefinitely waiting for 2 more threads to show up and wait on this barrier. Because the barrier has that number it has to have before it releases. And the other function we'll use is pthread barrier wait. So this is what the threads will be calling, and they'll be calling it on the same barrier as one another. That we'll have to create one of these. Okay, so we don't have any files yet, so we're going to copy the files from lesson2, and we can just leave it called race. It doesn't really matter.
We're still racing things.
Yeah, so it's going to be a slightly different race.
We could have called it gate race or something.
Okay, so what we need in this result, we need another pthread barrier type, and we'll call it a gate. Sure, why not? Okay, and if we're going to store the first thread that's going to arrive, then we should have a place for it to store that. And in order to know whether or not a thread has arrived before, we're going to count how many have gone by. Now, in order for how many to be usable, we'll have to set it to 0, but we'll do that in main before we start creating the threads. Now, let's just go ahead and do the main fix up, because otherwise I'll forget to do that. Okay, so r.howmany is 0, so that's no threads have gone by yet. And instead of pthread mutex init, we still need that because we'll still use the lock. The lock is the resource that they're going to be essentially contending for after the barrier releases. But we'll also need to init the barrier, and that's r.gate. And we need to know the number, the count on this is going to be ntd, the number of threads, so that we have to create the same number of threads as we need to have waiting there. So that's why we defined it as something that's fixed. We could change ntd, and then we'll change there too. Okay, now the other thing that we'll need to do at the end is we need to destroy the barrier. I'm pretty sure this didn't
print the first ID.
Yeah, and then we can destroy. Yeah, this I'm just making sure that it only needs one argument, which is the barrier to destroy. Oops. Okay, so so we can have the first ID. I mean, we could do it in one statement with like this r.first ID, comma r.last ID, and then we can just do %d space %d. So it's still gonna have one line per execution. So it's gonna output one line, and there'll be a space in between. we wanted to put a tab in between.
Yeah, let's do a tab,
/t like that. Okay, so what we should be ready to do now is fix up the thread so that they actually wait on the barrier, because otherwise it's not getting much use. So the first thing the thread's going to do, I mean, it can convert its argument, that's fine, but then it'll wait on the barrier. So and then it's going to try and acquire the lock. If it acquires the lock, now it has to do more than just what it did before. If it was the first thing, so we need to see how many have gone by, which is going to be set to 0. So if how many is equal to 0, then it's the first thread. But we're gonna do something in a second, which is why I have this extra parentheses. So r.first id gets to be tid. Okay. Now this needs to be incremented each time, or at least needs to be incremented the first time. So what we do is the post increment, and post increment causes r.howmany to be read, and then incremented after it's read. So it's still comparing the way r.howmany was before it incremented it, and it's going to compare that to 0. If I put this, this one's called a pre-increment. If I put ++ r.howmany, it would increment it first and then return that value, and then that would never be equal to 0. So if we wanted to do a pre-increment, we would have to start it out r.howmany as -1. That should be valid, but there's no need to do that. We just basically use the post increment. I'm just saying there are different ways to achieve that, and everyone's going to basically overwrite the last ID, and just like we had before, and then the last one that modified it will be the one that's there by the time the printing happens. Right. So then, of course, if you don't unlock the mutex, then nobody else will continue. All the threads will be waiting on that mutex because it would be locked. But so of course, every thread that locked it has to unlock it, and then exit the thread. So then it would be joined to here in this second loop here, and then we'll destroy the mutex, we'll destroy the barrier, and then we'll print our results. So this won't actually compile because barriers are not there by default. But let's see what error message we get. We get, all sorts of nonsense. So what we have to do, we have to change our make file. Okay. We need to basically add an additional C flag, and basically this C flag is to define POSIX C source equal 2008-09 L, and then
what's that number all about?
That's, I guess, the year 2008, month 9, and yeah, so that's
okay.
That's basically the version of that specification. So now it compiles because we're using the version of the specification that has barriers. And if you do man like pthread barrier wait again, probably one of these will tell us pthread barrier wait is part of the barriers option. So barriers is not a core part of the specification. It's not required to be implemented. Linux, of course, at least in the generic like CentOS, what we're running here, has barriers option. It could be that if you're on a certain embedded system, it might not have the barriers option, or if you're on some slightly less than, mainstream something, it might not be there. But it's here in this one. I mean, we're running this version of Linux kernel. So now basically we've built it. I mean, we can see that it compiles, cleanly with no warnings. Okay, so so we get some 0 on.
Right. It was interesting that we got 7 and 6 like that.
Yeah.
Now, what you'll see, like, the more you run this, is that even though we have a barrier in place, it's still not completely without bias. And why would you say that is?
I mean, it's just
the way
they're not implementing it in such a way that it's fair,
Truly fair.
I mean, it's not supposed to be. It's just it's making sure that that it's functionally correct. You know, the things stop on the barrier, and I mean, there's something actually you can do. There's a special thread in the barrier wait. You can actually test the condition of the return on that and see if you were the special thread. Only one of them is. You should be able to run a printf in it. Hopefully.
We'll see.
I was special. Okay, and then we'll put its number. Okay, and then just TID. Okay.
Okay.
Interestingly, the special one is matching.
Yeah, see that?
So that's the one that gets to run the serialized code, is the one that was special. So they set it up so that when you have a barrier, you can easily have an if statement around the return on the barrier wait and serialize your code that way. So it's, in any case,
It's a little something about the
you can have serialized code inside your
structure.
thread. Yeah, inside your threading. So in any case, yeah, that's what we got this lesson. we're running under our time limit, but that's better than running over. So
For
we'll
certain.
stop there.